Consider how changing a rock's environment promotes weathering. So if a rock is subjected to a new temperature and pressure, then it's more likely to be susceptible to weathering. So rocks formed at high temperature and pressure, for example, cooling off in a magma chamber deep below the surface, or a metamorphic rock that forms at very high pressure and temperature deep in the earth, it may not be stable on the surface. Those minerals form at a specific temperature and pressure, and when they come up to surface pressure and temperatures, they lose stability. They start to break down. So those rocks interact with the atmospheric oxygen in a different way. They're not used to being exposed to that. They're used to being deep inside the earth. So water can break down the mineral bonds easily or more easily. Okay, bottom line here, rocks formed at high temperature and pressure may not be stable on the surface. Okay, because they interact with oxygen, they interact with water, and they're breaking the minerals down. What happens when rocks dissolve? Okay, so observe the features that form when rocks dissolve. These photographs here are of limestone. So what's going on here? We have the formation of pits, right? The little divots or holes that are here. We get rounded edges and corners, wide joints, and it looks like the joints would capture runoff, right? So that means the water's going to go to the lowest area possible, and if it falls in one of these joints, it's likely that the water is going to run down that joint, just further widening it and making it deeper over time. So this is one way that calcite dissolves in water. We start out with calcite, this CaCO3, right, calcium carbonate, plus carbonic acid, right? This is a weak acid that's in water. So we add a weak acid to our calcite, which is what limestone is made up of, and the result is calcium ion. So we freed up that calcium from the calcium carbonate. What gets left behind is a bicarbonate ion in solution. All right, how do rocks oxidize near the Earth's surface? So you don't need to know this formula. It's in the book. You don't need to write it down. But we start out with the mineral pyroxene. Okay, that's this 4 iron SiO3 plus oxygen. So we're oxidizing it, meaning we're reacting it with oxygen. And then the result of that is hematite and silica in water. Okay, so as a result, hematite is an iron oxide. That's this Fe2O3 iron oxide, which just means it's oxidized iron, which is the same thing as rust. Okay, this is why the beautiful red rocks in Sedona are red, and this is why Mars is called the red planet. It's covered in hematite, just oxidized iron, and that happens when we react pyroxene with oxygen. Okay, how does the process of hydrolysis operate? Well, we're breaking down feldspars and turning them into clay. Okay, so we're chemically weathering these rocks, and potassium feldspar, this K feldspar, is very common in granites in particular. They're the pretty peach-colored crystals that form in granites. So when you react that with water, the result is kaolinite, which is a clay. It's a very useful product that gets used in building materials and all sorts of things. We get potassium that's dissolved in water and silica that's dissolved in water. Okay, that's those two chemically weathered processes are oxidation and hydrolysis. So remember, oxidation has to do with iron. You're oxidizing iron, you're rusting the rock, so you're going to have iron, Fe. And then the process of hydrolysis, you're breaking potassium feldspar down into clay. So you can think of it as weathering granite into very fine clay. How weathering makes the ocean salty? The simple answer to the question, why is the ocean salty, is just that the land surface is being broken down through the process of weathering, and the minerals are being redistributed from the land into the ocean. So over millions of years, this creates a really high concentration of salt and other minerals in the ocean. The main ions that create the salt in the ocean are sodium and chloride, and those ions get released through the process of weathering. So as groundwater moves through the surface of the earth, as materials on the surface are exposed to water and oxygen, that water chemically reacts with the rocks, and those dissolved ions get carried by water to the oceans. The salt concentrates in the oceans, and as evaporation occurs, the water becomes even saltier, because as you evaporate off that steam, the salt does not evaporate. The salt or any minerals that are in it remain in the water. So it's just getting saltier over time. From a quartzite. And then each mineral in a granite weathers differently. So you've got quartz, which is very resistant. Then you've got potassium feldspar, which through hydrolysis turns into clay. So even within the same rock, you can get different types of weathering. Some rocks weather into angular blocks. Some rocks weather into small chips. So again, it just has to do with how strong the rock is and how it was originally deposited. If it was originally deposited in fine, small layers, it's more likely to break into chips. If it's a resistant, very hard rock, it's more likely to break into angular blocks. So what happens when granite weathers? We just said that it weathers at different rates and has different products. So the feldspar weathers by hydrolysis into clay minerals. Those clay minerals can accumulate in soil or muddy environments, so you get these very fine clays deposited. And then we have mafic minerals. Those are the dark iron-rich or magnesium-rich minerals in the granite. Those mafic minerals form clay minerals as well, or they oxidize into hematite. While the quartz is very hard, it sometimes weathers into quartz grains. So it takes a very long time because it's a really strong, well-bonded mineral, but over time it can weather into quartz grains. Okay, so this bottom picture is an example of quartz grains that over a long period of time turn into quartz sand. So at a sand dune, for example, you'll find perfect spheres of quartz sand, and you can just imagine those originated in a granite as part of this very solid rock that had to weather into pieces of quartz, and then those pieces of quartz broke into smaller pieces. Those smaller pieces were rounded out into these spheres over so many years. That's part of why I think dunes are so interesting, and why something as simple as sand can be so cool, because it's got this amazing long history. Controls on how minerals weather. So some minerals are very strong, some are weak, and that has to do with chemical bonding. How are the minerals put together on an atomic level, on a tiny level that determines the shape of the crystal and how strong it's going to be. So if we look at halite, which is just table salt. Halite has ionic bonds, and it's soluble. Okay, so if you have water falling on a soluble mineral, you know that it's going to dissolve that halite. Okay, and then in contrast, quartz has covalent bonds, so it's significantly less soluble. It has very strong bonds that are holding it together. Okay, reactivity has a big part to do with how minerals weather. So again, limestone, which is just calcite, is soluble. It reacts with weak acid, so it's easy to dissolve, whereas most sandstone is made of quartz. We know that it has covalent bonds that make it less soluble. So its reactivity is lower. It's harder to weather a sandstone or a rock that's made from this quartz sand. Okay, so if we're looking at these different types of bonding, we can look at it as sort of a exchange here. So the example for ionic bonds is I'm letting someone borrow a $50 bill, right? I follow them around while they have it because I don't trust them so much, but I let them borrow it. I let them hold on to it, okay? This is equivalent to what happens in an ionic bond. I would be giving up an electron, but I'm staying very close, okay? As opposed to covalent bonds where they share an electron, okay? So if I am giving somebody a $50 bill, well, I'm not letting go of that $50 bill, okay? We have to share it. We both have to hold on to it at the same time. It's a much stronger bond. This lovely photo was taken near Bluff, Utah, and it's here to demonstrate factors that influence weathering. So you can see that there are at least two rock types we're looking at here. So they're made of different things. Their composition is different. Composition plays a big part in determining how a rock is going to weather. What minerals is it made up of? Is it made up of quartz that is less soluble, or is it made up of calcite that is quite soluble, for example? Right? So these two have different compositions. This upper rock seems to be more resistant, right? It's forming these cliffs, so it's not dissolving or breaking down, whereas the lower rock seems to be breaking apart more readily. The type of rock will determine whether it is more or less susceptible to forming recesses. If it's a soft rock, then it's more susceptible to forming recesses. If it's a harder rock, meaning it has been better cemented, it has stronger minerals holding it together, then it's more likely to form cliffs. Okay, the surface area involved is important. Remember, the more fractures or joints there are, the higher the surface area exposed for weathering. Discontinuities, other factors that influence weathering. We've got climate, the side of the mountain range, hill slope orientation, steepness of slope, and time. So climate includes precipitation, whether that's rain, snow, sleet, temperature, whether it's freezing or not. The climate is very strongly influenced by latitude, elevation, ocean currents, everything we talked about basically in Chapter 13. You'll get more chemical weathering occurring in warm, wet climates. And the climate can vary across a mountain range. So the side of the mountain range here is referring to particularly a rain shadow desert. So we've talked about these before. You'll have warm, moist air being pushed up into higher altitudes across mountain ranges. where it cools and condenses and precipitation will fall at the peak or on one side of the mountain, and then on the opposite side of the mountain range, there's no moisture left in the air, so there's no more rain to fall. So the other side will experience significantly less weathering if you don't have precipitation occurring there. Hill slope orientation determines the amount of sunlight and heat that that area receives. It also determines the type of vegetation, the degree of soil development, and moisture retention. So that plays a big part. Steepness of slope is also important because that determines whether you will have runoff versus infiltration. So are you feeding the groundwater? Is it soaking in, or is it just running across the surface? Are you able to retain soil, or does that get carried away with the runoff? And then similarly, the steepness of slope will determine what type of vegetation will be able to grow there. And then finally, time. With additional time, you're able to have increased soil development. Let's observe how weathering produces rounded features. So we're starting off with sharp angular edges. So typically we think of rocks that are initially broken off of their source as being very angular, and then over time they're rounding out as they get further away from their source. So edges and corners begin to smooth. As that angular piece of rock falls down the hill or falls into a river, and you've got water with sediment beating on those harsh, sharp, angular edges, they start to wear down over time, and then eventually there are no sharp edges or angular features. So if you want to prove this to yourself, an easy experiment is to just grab a couple sugar cubes and put them in a jar. So they start out perfectly angular, made up of little grains of sugar, just like a sandstone would be made up of grains of sand. And you shake it, and the first thing that happens is you lose all of the sharp edges, and then it rounds out. So you end up with a sphere. This feature on the bottom left is called a weathering rind, and this happens in particularly in sandstone. And then we also have spheroidal weathering, where these boulders, these granite boulders, have undergone so much exfoliation, they're now this nice rounded shape.